Well, all right, let's get started. Thank everyone for joining us today. For those of you who don't know, I'm Suzanne Staggs. I'm the current director of ACT, and I'm joined here by 5 of my colleagues. Mark Devlin, who's the deputy director of ACT, and he'll be moderating the Q&A session today. And then our 4 speakers, Emmanuel Sean, Simone Ferraro, Stefania Amodea, and Nick Battaglia. So ACT is the Atacama Cosmology Telescope, established with NSF funding in 2004 to investigate the cosmic microwave background with the specific aim of making high fidelity, high resolution maps of the CMB. And this is the 3rd in a series of webinars to describe science highlights from our recent data release. And this one's going to showcase the power of the high resolution of the ACT data to impact our understanding of the evolution of massive structures in the universe well after the primordial epoch of the decoupling of the CMB. Please use the webinar Q&A feature, which is at the bottom of your screen, to submit questions at any time. However, since we aim to keep today's event to an hour in length, Mark will hold those questions until the Q&A session, which will be after the 4th and final talk. Therefore, please include the name of the speaker and even the slide number with your question, if possible, if you want to direct to someone. And if at the end you want to hear more, we recommend you invite the speakers to give talks at your institutions. And with that, here's the first speaker, Manushan.
Great. So thank you so much, Suzanne. We're really excited to present to you these 2 ACT papers which just appeared on the archive last week. And so these papers present new measurements of the kinematic and thermal Sunyaev-Zeldovich effect from a sample of low-mass galaxy groups at high redshift. And I thought I would start off by explaining our goal here. And the motivation for these projects is this missing baryon problem. And so if you look at realistic hydrodynamical simulations, what you find is that the gas profile, this distribution around halos, is much more extended and spread out than the dark matter halo profile. And this has to do with feedback effects in galaxy formation. So specifically, supernova explosions and active galactic nuclei inject energy and momentum into the gas and pushes it far outside of the Vero radius. Once the gas is pushed far outside the Vero radius, it's typically too diffuse and cold to be detected directly in emission, for example, through X-rays. And because this gas is not seen, this has been called the missing baryon problem. Now, we'd like to think of it more as a missing baryon opportunity, an opportunity to learn about galaxy formation and the amplitude of feedback by measuring those gas profiles and how extended they are. Now, this is also an opportunity to actually learn about cosmology. And the reason for this is straightforward. Baryons are about 15% of the total matter in the universe. And so if you don't know where 15% of the mass is, your uncertainty on the matter power spectrum is as much as 30%. And indeed, if you look at this power spectrum plot on the right, on the scale of halos, what you see is if you compare those different curves from different hydro simulations, their scatter is about 30%. And this is the largest theoretical systematics. If you want to analyze weak lensing data from the Rubin, Roman, and Euclid observatories, which are going to give us not 30%, but 1% precision measurements on these scales. So our goal here is really to measure those gas profiles far outside the Vero radius around low mass halos and at high Z, which are extremely difficult to measure in any other way. And this is a place where the CMB can shine. So if you could please advance to the next slide. The properties of the gas around these halos get imprinted on the CMB. Oops, apologies. The properties of the gas around these halos get imprinted on the CMB through a number of effects. 2 of them are the kinematic and thermal Sunyaev-Zeldovich effect. So these are simply the change in the energy of CMB photons as they bounce off moving free electrons in the gas. And these electrons are moving for 2 reasons. One is the halo itself has a bulk velocity. And so this bulk velocity produces the so-called kinematic Sunyaev-Zeldovich effect. And this effect is proportional to what fraction of CMB photons do bounce, which is encoded in this optical depth to Thomson scattering, which is linear in the electron and therefore the gas density. The other reason those free electrons are moving is because they have thermal motions. And so this is called the thermal Sunyaev-Zeldovich effect, whose frequency dependence is known from first principles and also depends on that same optical depth to Thomson scattering and therefore gas density, but also depends on the mean squared thermal velocity of the electrons and therefore their temperature. So if you can measure at the same time kinematic and thermal Sunyaev-Zeldovich effect, you have measured the gas density profile from kSZ and the gas thermal energy or pressure from tSZ. And so not only have you found those baryons, but you have a handle on their thermodynamics. Now, there's a few properties of these effects which make them really unique and well suited to do this. One is that they're effectively independent on redshift. And this lets you probe objects at very high distances and high redshifts. The second is that this kSZ scales linearly at the gas as the gas density, as opposed to square for something like X-rays, and without a dependence on temperature, unlike thermal SZ. And what this means is that this is particularly suited for the outskirts of halos and for low mass halos. So we think that kSZ is really a unique probe of this regime, high Z, low mass halos outside of your radius, which is somewhat uncharted territory and which we can now explore. So let me now describe the measurement we performed. So we combined a galaxy catalog from the Baryon Oscillation Spectroscopic Survey with temperature maps from ACT and Planck. Specifically, we used this CMass or constant mass galaxy catalog, which is a large sample of galaxies, each of which roughly traces the center of galaxy groups of about 10 to the 13 solar mass. As you can see on this footprint plot, the bus sample overlaps very well with our ACT data. And the maps we used are the following: co-added maps of ACT DR5 and Planck at 150 and 98 gigahertz, presented in NES et al. 2020. And in order to check for dust contamination to the thermal SZ signal, we also used internal linear combination maps of our ACT DR4 maps, described in Madhavacharil et al., Cho et al., and Ayola et al. So once you have this galaxy catalog and those maps that overlap so well, you can extract the thermal SZ signal by simply stacking your temperature maps at the position of your CMass galaxies. For the kSZ, though, the situation is a bit more complicated because this dependence on the bulk velocity of the halo, this linear dependence, means that half of the galaxies moving away or towards you will have a kSZ signal with a different sign. And so if you simply stack all this, you average down the signal and you will null your kSZ. So to avoid this issue, we use the fact that we have redshift for these CMass galaxies, and therefore you can put them in a 3D box. So you would be sitting here. And when you do this, this gives you a handle of the 3D matter density field inside that box. And in linear theory, this matter density field can be directly converted into the velocity field. And so when you perform this operation, you are left with individual estimates of the halo velocities, which are here color-coded in red and blue. So once you have those individual estimates of velocity, you can now weight your stack with those velocities and avoid the cancellation of the kSZ signal. So this is exactly what we did. And so what I'll do now is show you basically the raw output of those stacking procedures to show you what you can see by eye about the gas properties of these halos. So if we start with the thermal SZ effect, here on the left, you see what happens if you stack on our 150 gigahertz map at the position of CMass galaxies. The outer circle shows you the virial radius of those halos, and the inner circle is the beam, so the resolution of this map. So what this shows you is that the beam of these ACT maps is sufficient to resolve really well the profile of the gas. And you should see by eye this dark thermal SZ decrement, which extends past the virial radius. And so you are seeing by eye the gas pressure profile around those CMass galaxies. Another feature that probably stands out is this bright spot at the center of the halo, consistent in size with the beam. And this is dust emission from dust within the galaxies inside these halos. And since we want to produce a thermal-IZ measurement that's clean of dust contamination, as Stefania will describe, we followed two approaches. One, measure this dust emission directly in high-resolution, high-frequency Herschel data and effectively subtract it. And two, use an internal linear combination of our maps, which is constrained to deproject a fiducial dust emission. And so when you do this, you are left with this thermal-IZ profile without dust contamination. So this was the thermal-IZ signal. Moving on to the kinematic SD signal, where your stack, again, is weighted by the line-of-sight velocity estimates. These are the raw outputs at 150 gigahertz and 98 gigahertz. So no filtering was applied to these maps at this point, apart from the beam in the map. And even though no filtering was applied, your eyes can surely still pick up this bright blob at the center. And so you are seeing by eye the gas density profile around these galaxies. And the fact that you're able to see it by eye without any filtering shows how high the signal to noise in this measurement is, 6 to 8 sigma. So again, a high resolution measurement, high sensitivity measurement of the gas with a resolution sufficient to resolve the gas profile. Other features that you see in these maps that are useful to understand now, so you can understand the processing that we applied to them, Simone will describe, is this large gradient from blue to green that you can see across both maps. And this is basically a residual CMB gradient. So on the larger scales, our noise is dominated by the primary CMB. On the other hand, on the smaller scales, those blue and green specks that you see are different in the two maps, and that's because they're mostly due to detector noise, which is uncorrelated across those two maps. So to summarize the raw outputs of these stacks, we have stacked on ACT and Planck maps at the position of CMAS galaxies. And thanks to this high resolution and sensitivity, you can see by eye the gas density, the gas pressure, the dust emission around those halos. And just to give you an idea of how extended those profiles are, if you take a Hubble image of a CMAS galaxy, this square hit here would fit within the central pixel of this map. I will now pass it on to Simone Ferraro, who will explain to us what processing was done to these maps and what we can learn from them.
Great. Thanks a lot, Manu. And yeah, so let's jump right into it. So Manu showed the measurements, and now to sort of interpret these measurements and do something quantitative, the first thing we are going to do is filter the maps. And that's precisely because of what Manu was showing, that primary CMB on large scales leads to these large gradients in the map, which act as noise, while on the small scales, the noise is dominated by detector noise. So we are going to use what we call compensated aperture photometry filters. These are filters that measure sort of the average signal in a disk, shown in purple here, and subtract the mean signal in an adjacent ring of equal area. So here we show a schematic image of the three filters at three different apertures. And so we are going to apply these. We're going to go to each stack and essentially apply these filters, centered at the center of the galaxy. All right, so the plot on the right, there's a lot of to unpack here, so we're going to take some time to describe it, but it's one of the most important plots in this talk. So that shows the kSZ signal once filtered, which comes from the map that the stack that Manu just showed. This is the kSZ signal once filtered with this set of filters. Well, actually, a few more of them. of them. All right, so first of all, you know, the data is the blue and purple points. They are at 150 and 90 gigahertz respectively. Turns out they're fully consistent, and the small difference you see here is due to the different beams of the maps. And once you reconvolve the maps to the same beam, as we show in the null test section, they are fully consistent. Okay, so you can think of the output of this filter output as a sort of cumulative profile. So this just tells you that as you're close to the center of the halo here, a small aperture, you see very few baryons, and then as you go out further out in the halo, past the virial radius and out to about 3 virial radii, which is where we can measure things too, you find more and more baryons. Okay, so to just this is intuitively sort of hard to understand without any reference. So we thought we'd plot what the baryons would look like in these dashed lines if they followed the dark matter, which is known to have roughly an NFW profile. And note that this NFW profile shown here has been convolved to the same beam and filtered in the same way as the maps have been. So this is really apples to apples comparison. The virial radius is indicated by these two vertical lines here, a little bit below 2 arc minutes. And as you can see, it's very, very clear and very significant that there is a large deficit of baryons within the virial radius here. This, of course, is the well-known missing baryon problem that, in present galaxies, as Manu said, you find only a small fraction of the cosmological abundance of baryons within the virial radius. But this is a very, very striking feature, and you see that the gas actually has been rearranged and pushed out such that these are, remind you, cumulative profiles. So you have to go to about 3 virial radii to recover the cosmological abundance of baryons. We think this is one of the main results, and is kind of very important because you see the gas has been pushed out and rearranged by order unity, by very rich physics beyond just gravity. And so you really have, a order unity rearrangement of the gas profile, and this will tell us a lot about, feedback processes and the rich physics behind this, which is, feedback, star formation, accretion, adiabatic mixing, etc. And, the interpretation of this in terms of physical parameters will be the subject of Stefania and Nick's talks. Okay, so while Manu said, this is technically a 6 to 8 sigma detection of kSZ, so detection over null, we actually can tell the difference with NFW to more than 90 sigma. In fact, I think delta chi square is square root of that is like 96. So this is really significant, and you really should think of this as almost percent level measurement of what the gas profile looks like. So it's an incredibly powerful measurement. And as Manu said, of course, we also measured the tSZ, the thermal Sunyaev-Zeldovich effect. So this is a very similar plot to the one before. It's just, it looks different from the tSZ profile is actually not that different from the kSZ. However, as you all know, it shows up as a decrement in our frequencies at 90 and 150. So this is kind of flipped upside down compared to what the kSZ curve look like, but it's not that different. And as a reminder, the tSZ measures the gas pressure. So this is thermal pressure, actually, to be more careful. And the last thing I'm going to say is that these measurements, as we've seen in some of the stacks, is sensitive to the dust emissions from these galaxies. And we have these two ways. What I'm showing here is this internal linear combination map where CIB has been oh, oops. Actually, sorry. Yeah, I realized the slide didn't move. Okay, great. Yeah, again, here's the kSZ, is the tSZ stack. And as I was saying, here the dust has been deprojected using a fiducial model. However, we also have a model in which we jointly fit the ACT inertial data, and that gives completely consistent results. So it gives us confidence that this actually is robust to dust emission. Okay, so now we've measured both the density and pressure. So the ratio of the two is really just temperature, as we show in these equations up here. The tSZ decrement is proportional to the optical depth of the cluster, which is essentially just the integrated number of electrons times the gas temperature. While the kSZ is directly proportional to the gas density. Therefore, if you divide the two and take some care about, beams, etc., you can get an estimate for the temperature in each aperture independently. And at the same time, we also calculated what we expect the virial temperature to be for a single isothermal sphere of the same mass, and that's the line, the dashed line here. So first of all, as you can see, we get something that is of order the virial temperature is actually slightly lower and decreasing with radius, which is what we expect. And this is just saying that the gas physics in sort of actual clusters is more complicated than just a singular isothermal sphere. But we do believe this measurement, and in fact, with proper modeling and physical models, Stefania will show an even better measurement, sort of even more robust measurement of temperature later in the talk. All right, finally, to interpret the measurements, we need a covariance matrix. And as you might have guessed, looking at the data points, they are not all independent. So on the left, I'm showing covariance matrix for the kSZ effect. So this is, the numbers here are the aperture in arc minutes. And as you see, the small apertures are almost uncorrelated between each other. While as you go to larger aperture, they become more and more correlated, and that's due to this large scale CMV modes that are common between all of the apertures. So this correlation is very important, that has to be taken into account. And since CMB is present in both 150 and 90 gigahertz maps, that also the cross covariance between the two is non-zero. On the right, I showed the thermal Sunyaev-Zadovich covariance matrix. It's more diagonal here because detector noise plays a larger role compared to primary CMB. However, the off-diagonal components are also important and need to be taken into account. Okay, so this is obtained by Bootstrap. In this work is accurate to considerably better than 10%, but we forecast that for future measurements, we'll need to actually fully simulate the data set because of overlap between different filters. All right, so finally, we want to say that we did a number of pipeline tests, and that can be summarized with working at the pixel scales requires considerable care in how you do the reprojection, how you do rotation, how you do interpolation, because you want to conserve flux. And this is something that we have shown in simulations that I won't fully describe all the tests here, but be reassured that we tested this to much higher accuracy with noiseless simulations, so much higher accuracy than what we need. And in fact, in the simulations, we can even see the effect of the two halo term and estimate it that will be around 20%. This is just saying that this red and blue curve actually go above the one halo profile shown in black here, and that's because of the two halo term. But we have ways to isolate the one halo term only, and that indeed is the green curve, and it agrees perfectly with the input profile. So in my last slide, I will conclude that to be able to trust our measurements, we have to perform a number of null tests. On the left, I just show one of the most important one, which you may wonder, the tSZ signal is often larger than the kSZ for a lot of our halos. So is there any contamination of tSZ into kSZ? And the answer is that contamination is really consistent with null. So that's great news. And to obtain this, by the way, we had to cut out the most massive clusters. So we have a mass cut. We don't include very massive clusters that could potentially contaminate the signal. We also have a very large number of actual null tests. some of which are shown here. So for example, we tried different velocity reconstruction algorithms. We shuffled the velocities, we did tests on Mach. We also look at consistency, again, as I said, between the 150 and 90 frequencies when they are brought to the same beam. We look consistency between daytime data and nighttime data, and finally between different ways of dealing with foregrounds. And they all pass, so then now we have confidence in our results, and so now we can hear about the interpretation of these measurements from Stefania and Nick coming up.
Oh, thank you, Simone. We have indeed an amazing data set, and that we can use it to explore and constrain different models of the distribution of the density, the pressure, and the temperature around galaxies. With this purpose, we must forward the profile modeling to the observations that Manu and Simone just described. And to do so, we've developed a pipeline called MOPSI-GT, Model to Observable Projection Code for Galaxy Thermodynamics. And I'll briefly show here a scheme of how it works. The pipeline takes in input the 3D theoretical profiles. We have here an example of the gas density in blue and the thermal pressure in red. And we have the halo gas profiles and the contribution from neighboring halos too. So each profile is a sum of a 1 halo and a 2 halo term. We have this projected, we project the 3D gas profiles along the line of sight. And so we get 2D projected density and pressure profile, and we convolve then with the same beam with which the ACT plus Planck maps were convolved. Then we reproduce the same aperture photometry filtering that has been applied to the data and that Simone described in his presentation. And, oh, sorry. And we finally obtain the SZ observables. From the gas density, we obtain the kSZ observable. From the thermal pressure, we obtain the tSZ observable that we can directly compare to the observations that Manu and Simone presented in their presentation. Now, the simplest model that we can explore is a generalized Navarro-Franken-White profile of the gas density. As we've heard from Simone, baryons don't follow the dark matter, and we can use our kSZ observations to fit a gas density profile of this form with a free amplitude, a co-radius, and a power law index for the fall-off of the profile, and a free amplitude of the 2 halo term. And this plot shows the constraint we get on the GNFW parameters, and we discuss in the paper how these results change if we fix or not some parameters in the fit. And on the right, we have the best fit model for the kSZ and the 2 sigma ranges. And this is for the CMAS sample. So I want to stress again, this is composed mostly by group-sized halos, and we probe the gas density profile far out the virial radius. And in a few minutes, Nick will show how this model can be used to estimate the impact of baryons in galaxy-galaxy lensing. The second model we explore is a GNFW profile of the thermal pressure. And we use this time our tSZ observation. And in a similar way as before, we fit for the central pressure, the intermediate and the outer slope of the profile and the amplitude of the 2 halo term. As we've already mentioned, and as we described in the paper, an important systematic in the interpretation of the tSZ signal is the thermal dust emission from the CMAS galaxy. So we include a model for the dust contribution, and we constrain it using both ACT and also Herschel data at higher frequency. frequencies, and we get the constraints in blue here. In addition to this, as a validation test, we also use measurement of the Compton Y obtained from maps of the previous data release, ACT data release, where the dust was already projected from the map, and we check the consistency, and these are the results in red, and we check the consistency between these two sets of results. Now, these are two simple fully parametric models that we can fit to our data. But to learn more about the baryonic processes in the intergalactic medium, we explore a more interesting physical model. We call it OBB, because this was originally proposed by Ostreicher, Bode, and Babel in 2005. They proposed it for the intracluster medium of clusters. We apply it here to less massive group-sized halos. Briefly, the model assumes that the gas is into pressure equilibrium with the total gravitational potential, and the density, the gas density and the total pressure profiles follow a polytropic equation of state, where gamma is the polytropic index. The total pressure is composed by two terms, a thermal and a non-thermal component, and the non-thermal component is described by this radial profile, and we fit for the normalization parameter alpha. And this last equation describes the conservation of energy, where the final energy is equal to the initial energy plus a term that accounts for the feedback. And this is feedback from stellar, supernova, or also AGN. And here epsilon is a dimensionless parameter that quantifies the efficiency of the feedback, and m star is the stellar mass. Plus, the last term is the work received from the surface pressure when the boundary of the halos change. So we implement this model, and we fit this OBB model for these three parameters and get constraint on them using both our kSZ and tSZ measurements. These are these are our constraints, and I want to highlight the most interesting ones. For the feedback, we estimate the efficiency parameter with a precision of 10% within our model. And this value we get, 33 times 10 to the minus 6, is a considerable amount of feedback. We estimate that the energy injected by the feedback is 25% of the total binding energy of the system. We also constrain the amount of non-thermal pressure. We estimate the normalization of the non-thermal pressure profile with a 20% precision. And this number here, 0.3, indicates that the 30% of the non-thermal pressure, of the total pressure, sorry, within R200 is due to a non-thermal component. Now, using the posterior distributions of the model parameters, we obtain the tSZ and kSZ profiles, and from both of them, essentially from the ratio of the tSZ over kSZ, like in the same way as Simone described before, we can estimate the temperature profile, and this time we can use the posterior probabilities and consistently evaluate the uncertainty on these profiles. I show here in black the median, and the blue band is the 2 sigma range of the profile that we obtain from our fit. And this is the virial radius is here, and as you can see, we still get good constraints until twice the virial radius, and a bit more than twice the virial radius. And here we have that, if we want to have a rough comparison, we can look at the dashed gray line. That is the virial temperature of an isothermal sphere of gas with the same mass as the mean mass of our sample, 3 × 10⁻13. But this is a single number that we can use as reference. And that's about twice 10⁻⁷ Kelvin. But what's really exciting is that we can actually resolve the profile of the gas temperature and of other thermodynamic quantities as well. And we can do that for low mass halos very far out in a radial range that has been unexplored so far. And we can do this thanks to the combination of our very high significance kSZ and tSZ measurements. And with that, I'll stop here and leave the floor to Nick.
Great. So yeah, I've been tasked with talking about the implications for these really nice unbiased measurements of the thermodynamic profiles we have from inside the virial radius to well beyond the virial radius. So this is really a new observational window into the properties of the CGM and IgM gas. So the 2 things we decided to discuss within these papers are the impact on galaxy formation. And what these measurements actually do is really neat, right? They provide non-trivial tests of the current, state-of-the-art subgrid feedback models that are in these, massive, computationally expensive cosmological simulations of galaxy formation. The second thing that we decided to talk about was the impact on cosmology. And as you've already heard, right, baryons impact the matter power spectrum. They impact any sort of observable that depends on the matter power spectrum, especially on these small scales. And so what we were able to do is actually place empirical constraints on the baryonic effects on the matter power spectrum. And we related that to an observation that, well, I'll just show you what that observation is. So let's see, moving along. There we go. So we decided to apply our observations to this particular problem of that there's lensing models that are fit to large-scale clustering of galaxies, shown here in these lines, for the CMAS sample, are discrepant with actual observations of the lensing signal from these same galaxies. This is known as lensing is low. And it's still an open problem today. So we've already heard several times, and we've shown that the baryons do not trace the dark matter on small scales. We've heard the baryon physics, or we all know baryon physics is much richer than dark matter, and that this has implications on the matter power spectrum. And that's shown here in the bottom right, as if we look at the matter power spectrum of a full-blown simulation with baryonic effects, hydrodynamics, radiative cooling feedback, you can see that it is different from a simulation with dark matter only. In particular, on these nonlinear scales here, you can really see these deviations start to build up. And so what's really nice about our observations here of the CMAS sample is we can actually directly probe the baryon component, right? We have density profiles of the CMAS, of these CMAS galaxies, which is relevant not only for this particular measurement right here, because this is a measurement of this from the CMAS sample, but the masses of the CMAS galaxies are particularly important for these scales right here around k = 1, where you really see these baryonic effects start to kick in. So, this mass range that we're measuring for the CMAS galaxy is extremely relevant for these deviations in the matter power spectrum from a dark matter only simulation. So, what is our model? It's a very simple model. We take the lensing estimator delta sigma, which is just the average surface mass density within a radius minus the surface mass density at that radius. And we divide it up into 2 components. We have the dark matter component, which comes directly from, so it was that red line on the previous slide from the Lioto et al. paper. And we have our baryon component here, which comes directly from our kSZ measurements, which Stefania showed you. So these would be our best fit GNFW model. Now, what's really nice about this, the fact that we're just taking the average of the CMAS sample, is this average naturally encodes all the subtleties of that CMAS sample, right? It includes how many of those CMAS galaxies are satellite. That's going to be included in the average. Their average mass, all those properties, 2 halo components. That's all going to be within this CMAS or within this average sample of the CMAS sample of the CMAS stack that we made. So this is what this is often referred to as HOD convolved, or halo occupation distribution convolved. So we don't have to do any additional modeling when we're calculating this component. The next thing we do is we have to choose the normalization of this component. So we normalize this baryon component to equal the dark matter component at the furthest radius that we measure. And lastly, you can see here there's no additional term for the back reaction of the baryons moving the dark matter around. That in the paper we make arguments for why we think this effect is going to be a secondary effect compared to just the effect from the baryons. So here's the result right here. The green points show the measurement from Liotto et al. 2017. Here is the original model in red, and our correction is shown in blue. You can see here's the normalization, here's the normalization being stitched right at this boundary where these vertical lines are within these vertical lines is where we've actually made the measurement. So the blue line is the now new model with the baryon correction to the old halo model from Liotto et al. And this band here, this light blue band, shows you the uncertainty in that overall model. And what you can see is we don't get quite all the way down to these green points here. We get about half of the way there. So including baryons is definitely important, right? We can see it's a 50% effect on this measurement, given the model that we've proposed. But to fully reconcile this difference, there's probably several other things going on that were mentioned in the Liotto et al. Paper, like assembly bias, or maybe some cosmological parameters, as well as in general some of the HOD model, stellar mass to halo mass issues. So we're pretty happy with this, but there's still some more work. The problem is not completely solved yet. Moving on to the cosmological simulations, right? Cosmological simulations have been extremely successful, especially over the past decade, in producing and reproducing the stellar properties of galaxies that we see, right? The red fraction and blue fraction, the stellar luminosity function. Those are all, some really great successes of the current cosmological simulations that exist right today. Now, to get these results, though, right? These simulations required a little bit of fine tuning to reproduce, these stellar properties. In particular, they fine tune these subgrid models for, physical processes that are beyond the resolution of those simulations. In particular, things like feedback. And what's really nice is these current simulations have not been tuned to our particular measurements. So they've actually made predictions. So we can test these current cosmological models. And so we did that, right? We took profiles, as Stefania showed, 3D profiles. We run them through MOPSI GT, and we get our SC observables. And just so we've taken the illustrious TNG simulations and some old simulations that I ran almost a decade ago. So for the TNG, we did some additional things where we took, we tried to really model the CMAS sample. We did color cuts. We weighted the halos in the simulation by mass to best match the CMAS sample. So we did we did a pretty good job of trying to recreate the CMAS sample within TNG. And I just want to highlight Emily Mosier here, who is a top tier author on the second paper, who's not speaking because we just couldn't afford the time. But she did a lot of work here, especially on the TNG simulations. So here's the comparison. As you can see, the simulations this is kSZ on the left and tSZ on the right, or density and pressure. And what you can see here is the simulations actually do a pretty decent job in the inner regions here, but it's in these outer regions where you really see a stark difference between what we're measuring and what the simulations are predicting. Okay, now I'd be cautious, or just be a little cautious of doing chi by eye, right? These error bars, as we've seen with the covariance matrices that Simone showed, they are highly correlated. So, you know, if you want statistical, we provided you with some statistical numbers to show you how discrepant they are. So the PTEs for the density, it's actually not too bad. They're 0.12 and 0.14. So, you know, those are reasonable. And it's really in the density where these, you know, the PTEs for the density are 0, especially in these outer regions here. And so this is, you know, this region, these outer regions are actually the unexplored regions, right? This is where we're getting like really new measurements of the CGM and IGM properties in these galaxies out at these large radii. So it's not too surprising that, you know, current simulations would, you know, fail out here. Now this is just one, I'm not saying all simulations, right? We're just doing TNG here, but we hope to extend this to other simulations as well. Now, again, what's going into these profiles, it's not really too intuitive to understand in this fully observable space here. So what we've done is we've also provided in the paper 3D profiles. So we've taken these and gone back to the original inputs, so you can see and you can compare the 3D profiles. So our measurements are in blue here with the light blue band illustrating the errors from the best fit that Stefania showed for the GNFW profiles. And you can see here, this is why it's not so bad, right? You can see that even within these 1 sigma regions, right, you get the simulations. So, you know, pink is the BBPSS simulations, and TNG with 2 different selections are shown in green and orange. It's really when you get to the pressure that you see these discrepancies really start to pop out, even in 3D, right? And so what this tends to suggest, right, is the temperature in these outskirts is much lower, as well as the density being slightly lower. So the simulations aren't pushing enough gas out, or there's just not enough gas out there, and that gas just isn't hot enough. And, you know, this isn't an easy thing to predict, right? There were no measurements a priori, so this is really a challenging, these are really challenging scales. Why don't they match? Why don't the simulations match? Well, there's many different reasons why they don't match. It depends on how the energy is injected. It depends on how that energy is propagated through the CGM and IGM in these simulations. As I said, we hope to investigate this further in future simulations, and we hope, you know, these measurements can also be used to help refine, you know, current subgrid models so that they perform better, especially in these outer radii. So in summary, right, you've heard about these really nice measurements. You've heard about the significance and robustness of these measurements. You heard about all the modeling that we did in order to extract, you know, physical properties and profiles, and then you've heard a little bit about the implications for these measurements. Now, before we conclude, I'd just like to point out that they are, you know, these measurements are, you know, coming from advanced ACT, as we've heard, but we actually have more data in the can, and there's more data being taken. So I refer you to a previous ACT webinar where the timeline for ACT data is discussed. So in future data release, we hope to update these measurements. We'll hopefully get, you know, tighter error bars on both the density and pressure profiles of these halos. And we can actually extend this to different spectroscopic galaxy surveys. You know, DESI right now is on the sky, and also future CMB experiments should also help shrink the error bars. So this is just sort of the tip of the iceberg of what we can do with kSZ and tSZ measurements of groups and galaxies. And once we have these higher signal to noise measurements, right, we can even start dividing up our samples into very, you know, interesting things like galaxy type, redshift, things like that. So once we have, you know, we tend to, we're looking forward to being able to expand these such measurements in the near future. So with that, I'd like to thank everybody for your time and attention, And if you have any questions, please put them into the Q&A. And thank you.
Great. Well, thanks very much to our panelists. Every time I see this, I'm just really excited about the opportunities that are coming out. Where we were just a few years ago with the kSZ is just nothing compared to where we are now and going to be in the future. So we have a number of questions coming from the attendees. I would encourage people to continue to post questions there, and we will try to get as many answers as we can in the time that we have available. The first one's going to be to Simone. From your slide 10, I'm not sure you can flip back to that, but I'll just refer to it as I read it. If the difference between the 90-150 profiles is due to the beam size, why does it not converge at large scales?
Okay, so that's a good question. So on large scales, I think the points are, you know, fairly. I don't know if anybody could go back to slide 10. So looking at that, sort of the large apertures, they are pretty consistent already. I'm guessing what's happening here is also that you know, the beam convolution and applying the filter don't really commute. So you know, it's hard to see by eye, but I think they converge pretty well at large aperture. However, if you go back to the null test slide, I believe it's slide 15 or 16, the last slide of my talk. Yeah, this one. So here what we did in, I believe, purple is exactly like convolving the maps. First of all, convolving the maps to the same beam, and then repeating the measurement, doing aperture photometry filter, and then taking the difference. And as you see, the difference is consistent with null, like within the error bars, which is so consistent with it being just noise fluctuations, any difference that you may see. So I think that we were pretty reassured by this, that we are seeing the same signal.
Got it. Okay, next one is from Manu. Again, on slide 10 of that talk, the measured kSZ profile extends over 5 Vera radii, and I think that is correct, but you can verify that. Do you have an estimate of the gas mass fraction of the CMAS halos?
Right, so this is a very good question because, of course, what we'd like to know is how many of the baryons are within our beer, how many are outside. And there's sort of two difficulties for quoting a firm number to answer this question. One is this two-halo term. So as we start to go out to several virial radii, this cumulative profile that you see in the aperture photometry filter doesn't quite saturate because you start to see gas that's clustered with your galaxy cluster, but that's not in the halo itself. So that's one thing. And the other thing is the large scale noise from the CMB, which correlates all these aperture photometry filter points on large scales. And so this acts as an additive uncertainty to this number. So I guess we like to think of this kSZ measurement more of a measurement of the slope and the shape of the profile out to several Vera radii. And it's a little bit more uncertain to quote a value for the gas within our view.
Excellent, thank you. Okay, Stefania, this is a little bit of a long one, but I'll read it. While the distribution of galaxy stellar masses and redshift in the CMAS sample is relatively narrow, it still appears to span a significant range of inferred halo masses and angular size distances. Is this accounted for in the stacking measurements, or alternatively, is it included in the profile modeling, or alternatively, can it be shown to have a negligible impact on the analysis?
Yeah, so we account for that in the modeling, and we average our profile within on the stellar mass distribution of CMAS. And then we convert, we use a scaling relation to get the halo mass from the stellar masses. This scaling relation has an uncertainty. It doesn't have a strong impact on the analysis, but it's still there, and we plan to study in more details the impact of these uncertainties using simulations comparison. We've done this a bit with our TNG comparison using the two distributions, and we'll plan to do this in more detail in the future.
Okay, thank you. Nick, one for you. High level of feedback and non-thermal pressure is very interesting. I have two questions. how do ACT measurements compare to that of Planck in terms of the YSZ M scaling relation? And do both the ACT and Planck constraints suggest a high level of feedback and non-thermal pressure in groups?
Right. So to number one, we haven't done that direct comparison, right? This YM scaling relation is a measurement of integrated quantities. There is another paper coming out within ACT that will focus on integrated Y measurements of the CMAS sample. So that's something that could potentially be addressed in that paper. But we haven't addressed that here. Do both, I can't speak to the Planck constraints, but I would say that yes, these ACT results do suggest a higher level of feedback that's actually current simulations do provide. And that number that Stefania provided, that 25%, again, we're still refining that number a little bit, but it's still, that again suggests a high level of feedback compared to the binding energy of these halos, or I should say groups. In terms of the non-thermal pressure, yeah, I don't know if we have other measurements of the non-thermal pressure in galaxies of these masses, right? They're typically in, you know, the couple measurements we do have are in clusters. And again, the number Stefania quoted was that's the non-thermal pressure contribution all the way out to the virial radii, right? Where you do have stuff still falling in, and Daisuke, as you know, right, this does contribute to additional bulk flows and motions that do add to the non-thermal turbulent pressure support. And I use turbulence in a very not correct way.
Great, thank you. We're running a little short on time. We have a few more questions here. From Manu. What is the signal noise of individual velocity measurement used for extracting the kSZ signal? If it is small, do you expect some fraction of sign errors in your kSZ stack?
Right. This is a very good question because obviously the velocity reconstruction algorithm from the density field has imperfections. And so you want to know how these imperfections translate into noise or bias in the kSZ measurement. So this is something we've looked into in detail, and it turns out this is all encoded in one number, which is the correlation coefficient between reconstructed velocity and true velocity for a given galaxy. And in the main velocity reconstruction method we've been using here, that number is 0.7. So that means the reconstructed velocities are 70% correlated with the true velocity. So this has two implications. One, it means that our signal to noise on the kSZ detection is only 70% of what it could be if we knew the exact velocities. So that's a hidden noise. And in terms of bias, so if you know this number, this little r of 0.7, that's all you need to know to correct for any bias. And so this is what we did. Okay.
And here's a quick one for Simone. How was the normalization of the NFW profile set?
Right. So we know the approximate masses of these halos from both weak lensing measurements and actually from individual stellar mass measurements, which we then can use a model to convert to halo mass. So in particular, the NFW that you see is actually sort of the average of many NFWs with different masses that actually trace our mass distribution as inferred from a sort of stellar mass to halo mass relation. And is also, we checked that it has the right mean mass as measured by lensing. Then there is one more subtlety, which is the truncation radius of NFW. As you know, things depend a little bit where you truncate, but we checked that this actually doesn't make any difference, any qualitative difference to the statements that we make that baryons don't trace the dark matter, because the profile itself is a very different shape, and that does not get fixed by changing, say, truncation radius, for example. And we all know that NFW is not even accurate to a large, if you go to a larger truncation radius, because it actually gets steeper with radius.